Right. In the last video, we looked at Taylor series. And a Taylor series is a sum from n equals 0 to infinity of the nth derivative evaluated at c divided by n factorial times x minus c to the n. And if you expand out a Taylor series, if you plug in 0, you get the function evaluated at c divided by 1 times x minus c to the 0 is just 1. And then the next one is plus the first derivative evaluated at c divided by 1 times x minus c plus the second derivative evaluated at c divided by 2 factorial, which is 2, times x minus c squared plus dot, dot, dot. It's infinite. So a Taylor series goes on for forever. A Taylor polynomial stops. It just stops at some point. So instead of the dot, 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 it is just going to end at some point. And what this does is gives us an approximate Taylor series. So in that last example that we did, we could have, with the integral of cosine of x squared, we could have stopped at some point, and then approximated the integral. So as an example of the last time, we found that the integral from 0 to 1 of cosine of x squared was equal to, I have to find it in my papers here. It was equal to, we expanded it out and we got 1 minus 1/10 plus 1 over 9 times 4 factorial minus 1 over 13 times 6 factorial plus dot, dot, dot. But if we wanted to, we could approximate it by just stopping, so not doing the dot, dot, dot. And if we just stopped at this point, you'd have to plug this into the calculator, but you'd see that you'd get an approximate value of 9.05. Right? And this would be the Taylor polynomial. It's a Taylor polynomial, exact same thing as Taylor series, except for at some point we stop. All right, so let's do an example. So let's find, I'm going to call this t sub 2 of x for, I'll explain that in just a minute, for f of x equal to x to the negative 3/2. With a center of 1. So what t sub 2 of x means is that we are going to stop when n equals 2. So this is notation for the Taylor polynomial where it stops at at n equals 2. So I'll kind of just put a little bit of a note in here. The notation t sub k of x is a Taylor polynomial. It's a Taylor polynomial that stops when n is equal to whatever value you are given here, k. All right, so to find the Taylor series, notice that we don't have a Maclaurin series for anything like this. So we're going to have to do this by the definition, meaning we're going to have to use derivatives. So we're going to have to do this by definition. And that means that we're going to take the sum from n equals 0, but we're going to stop at 2. of the nth derivative evaluated at 1, c is equal to 1, divided by n factorial, times x minus 1 to the n. So this is going back to the definition of Taylor series. Okay, so we're starting with the function x to the negative 3/2, and I need some derivatives. So there's the function, the first derivative. So first derivative, the negative 3/2 comes down in front, and then I would have to, let's see, for derivatives we subtract 1, so to the negative 5/2. And then the second derivative, so for that second derivative, let's see, the negative 5/2 comes down in front, so that leaves us with 15, 3 times 5, and 2 times 2 is 4, x to the negative 7/2. And at this point, I can stop. I can stop because 2 is specified, so we're stopping at 2, so we're stopping at a second derivative. All right, and now I've got everything I need. I can just plug into this formula. So starting at 0, the 0th derivative is the function. Oh, just kidding, I still have to plug in 1. The function at 1 raised to the anything is 1. The first derivative at 1 would leave us with that negative 3/2, because 1 to the negative 5/2 is 1. And the second derivative, we would get 15/4, because 1 to the negative 7/2 is 1. Okay, so now I can just plug into this formula. I plug in 0. The 0th derivative is the function, and the function at 1 was 1. Divided by 0 factorial, which is 1, and then x minus 1 to the n, well, that's just going to be 1. So I'll end up with 1 for that first term. The second term, the derivative was 3/2, divided by 1 factorial, so that will just be negative 3/2, times x minus 1 to the first. Plug in n equals 2. So the second derivative evaluated at 1, sorry, I put x's down, those should be 1s. Evaluated at 1 is 15/4. That's now divided by 2 factorial times x minus 1 squared. So the Taylor polynomial is going to be 1 minus 3/2 times x minus 1 plus 2 factorial is 2. 2 times 4 is 8, so plus 15/8 x minus 1 squared. So there's the Taylor polynomial for that function. Next example, let's find Maclaurin polynomials. Actually, let's just find the Maclaurin polynomial. Maclaurin polynomial of f of x equals 1 over 1 plus x. And let's find this, the Maclaurin, so that means c is equal to 0. Let's make this a little bit more interesting by making it maybe like 3x. So 1 over 1 plus 3x, and let's find the Maclaurin polynomial up to a degree 3. And so what this means, degree 3, is that we want to stop when we get x cubes. And so we want to stop when n is equal to 3. All right, so taking the function 1 over 1 plus 3x, and looking at that sheet at the known Maclaurin series, the series for 1 over 1 plus x is the sum from n equals 0 to infinity of negative 1 to the n, but we don't just have x, we have 3x. So that would be a 3x to the n. Now we want to do this up to a degree 3. So for the Maclaurin polynomial, we'll start plugging in numbers, but we will end when n equals 3. So when n equals 0, we get 1. When n equals 1, it's going to be negative because of that negative 1 to the n term. And when n equals 1, we get 3x. There we go. 3x. Okay, so now n equals 2. That's going to be a positive. 3x squared, so 9x squared. The next one, so that's 0, 1, 2, 3, would be negative, and then we'd have 3x cubed. 3 cubed is 27, x cubed, and this is the point where we're going to stop. Because we wanted to find the polynomial, which is an approximation, it stops at some point, and only up to a degree 3.